So we've explained that atoms are made of three subatomic particles: protons, neutrons, and electrons. We have a model for how things might be organized in an atom proposed by Thomson, which was this plum pudding model, where we have this pudding that has a positive charge dispersed throughout it, and then we have the tiny negative electrons in the pudding. Okay, so the question is Thomson's plum pudding model correct? And as I mentioned previously, if this model was correct, you can see there are no empty spaces in the atom, so we would expect it to have the same density all the way across the atom. So here's the plum pudding model. Little electrons embedded in a big sphere of matter that has an overall positive charge. That sphere of matter probably made of protons and neutrons, right? Okay, is this the correct model for the arrangement of particles in an atom? Well, people wanted to test this, right? So around about this time, the beginning of the 20th century, there were a couple of people who were really interested in some new chemistry and some new physics called radiochemistry, or also referred to as nuclear chemistry. And three people that were really important in this area were Henry Becquerel, Pierre Curie, and his wife, Marie Curie. Ernest Rutherford was a New Zealand / Canadian / British physicist who was also interested in the concept of radioactivity. So what these guys had discovered was that some atoms spontaneously would emit very high energy particles. And there seemed to be two types of these particles. There were beta particles, which were fairly quickly recognized as being high energy electrons. They were just called beta because they were the second type discovered. And there were alpha particles, just called alpha because they were the first type discovered. And it wasn't really clear what alpha particles were. Now, I should point out that all of these guys that were studying radioactivity, nuclear chemistry, and nuclear physics were pretty interesting people. This was around the time of the First World War when they were doing that. So Marie Curie, for example, working with her husband, and then her husband died and she continued that work. She actually developed the first mobile X-ray facilities that were used for the first time in World War I, and she was actually responsible for the treatment of over 1 million soldiers during World War I, and she took many thousands of X-rays herself. And Henry Becquerel, he's the first guy who came up with the idea of using what we call radiotherapy to treat things like tumors. So these guys had important contributions, not just to fundamental physics and chemistry, but also to medicine. Now, remember we had these mysterious alpha particles that we didn't really know what they were. We knew that they were positively charged. And we knew that that positive charge was twice as big as the charge on an electron, and we knew that they were heavy, and that they were 4 times the mass of a hydrogen atom. And when one of these alpha particles was emitted by an atom, it was moving very fast, hundreds, thousands of miles an hour. So Ernest Rutherford had this idea: what about if you just took an atom and you slammed a beam of these very heavy, fast-moving alpha particles in there? Maybe you could break off a chunk and you could perhaps discover a new subatomic particle and maybe go on and win a Nobel Prize. Now, Ernest Rutherford did go on and win a Nobel Prize, but it wasn't because he was able to split the atom. Instead, what he did was he discovered how the 3 subatomic particles that make up atoms were organized with respect to one another. So, Ernest Rutherford asked 2 of his students to conduct what's now called the gold foil experiment. And what he was expecting was that if the plum pudding model was correct, the alpha particles he was going to fire at his gold foil would pass completely through the atom, totally undeflected. So he said that this would be like bullets through tissue paper. So he's going to take a beam of alpha particles, fire them at a gold foil, and the alpha particles should behave the same whether the gold foil is there or not. Okay, so what happens and how did he do it? So he gets a piece of radioactive material that emits alpha particles and he puts it in a lead box with a little pinprick hole in it. And the reason for doing that is because now he's just going to get a nice beam of alpha particles. And he fires this beam of alpha particles at a piece of gold leaf. And the reason for doing that is that gold is extremely ductile and malleable, and you can hammer it so it's only just a few atoms thick. So these alpha particles are probably going to only hit 1 or 2 atoms as they go through the gold foil. Around the gold foil, he puts a circle of material that's coated in, you guessed it, that material that glows when an electrically charged particle hits it. Now, what he's expecting is, if the plum pudding model is correct, the alpha particles will go straight through and the behavior will be the same whether the gold foil is there or not. But that's not what he found. What he found was that the alpha particles bounced around all over the place. In fact, some of them even bounced back behind the gold foil. And remember, the alpha particles are very heavy and moving very, very fast. So if some of them hit something that made them stop, turn around and move backwards, whatever it was hitting had to be incredibly dense. So he was expecting that the alpha particles were going to go through like bullets through tissue paper, right? And that's not what happened. Most of them did go straight through, but a very significant number were scattered to quite high angles. So how Rutherford kind of was explaining this was said, and this is not quite what he said, but it's close to it. He said it's like if you were firing a machine gun at a piece of tissue paper. Most of the bullets go straight through, but every now and then one will bounce back and hit you. So this was really, really weird. So the only way that Rutherford could explain this was, well, most of the alpha particles are going through as though nothing's there. So he's going to say, well, that must mean that most of atoms are nothing, right? So most of atoms must be empty space. And then he said that, well, every now and then some alpha particles get bounced back. So what that means is the alpha particles are positive. Every now and then they get deflected back, so they must be hitting something positive to repel them. And then he did some math on like how heavy and how dense that thing had to be that it was hitting. And he said that it has to be a tiny little speck of matter that he called the nucleus that basically has all of the mass of the atom. So something that's incredibly dense, really, 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 really dense, but doesn't take up a lot of space, but has a high mass. So this led to what we call the nuclear model of the atom. So in the center of every atom, we say that there is a nucleus, and that nucleus is positively charged. And this nucleus is very, very dense. Now, the rest of the atom takes up quite a large space, but it's mostly empty. It's not very dense at all. In fact, there's like basically nothing in there, right? So most of the mass of the atom, most of the matter in the atom is in this tiny little thing in the middle that's about 10 to the minus 15 meters across. And then the rest of the space that the atom takes up is basically like weighs hardly anything. Okay, so it's often said the nucleus of an atom is like a marble in the middle of a football stadium, right? So what the heck is taking up all of this rest of this space? It has to weigh almost nothing, and because the nucleus is positive, it has to be negatively charged. So you think about this for a moment and you're saying, well, what weighs almost nothing and also has a negative charge? I know, it must be the electrons, right? So the other stuff in an atom is the electron. So you've got two bits to the atom. There's the nucleus, which is positive and heavy, and then there's the electrons, which are negative and don't weigh very much, right? So that's what Rutherford, realized this as well. He proposed that the positive charge of the nucleus was because it contained, you guessed it, protons. And what are protons? Positively charged and heavy, right? And then he said that the small negatively charged electrons moved around the nucleus at a great distance from it, like planets from a sun, around a star. So here are the electrons out on the edge. Here's the nucleus with the protons in it, and then most of the atom is empty space. So that's why it's not very dense, right? It's empty space. Most of the atom is empty space. So you put all of this together, and it's kind of interesting. Atoms make up everything, right? Never trust an atom, they make up everything, right? Atoms are mostly nothing. So you end up with everything is mostly nothing, right? All of the matter that you see around you that looks so solid and so firm is mostly empty space, because most of every atom is the empty space between the nucleus and where the electrons are. Now, Rutherford couldn't get the nucleus to have enough mass to be able to deflect an alpha particle. It needs more mass. I wonder what else could be in the nucleus along with the protons to give it more mass. Well, you guessed it, it has to be the neutrons, right? So what we have now with the complete nuclear model of the atom is that the nucleus is made up of the neutrons and the protons, and then at a great distance from the nucleus are the very light electrons. So you have a nucleus that's very, very dense, but overall the atom isn't particularly dense because it's mostly the empty space between the nucleus and the electrons. So this is sometimes referred to as the planetary model of the atom, or also referred to as the Rutherford nuclear model of the atom. And it looks like the classic Big Bang Theory logo. Okay, so our modern up-to-date atomic theory considers that the atom is composed of a dense nucleus which contains nearly all of the mass of the atom. That nucleus is made of neutrons and protons, and then that nucleus is surrounded by very light, very small, negatively charged electrons that are a long distance from the nucleus. So all we need to really think about here is that protons and neutrons together make the nucleus. The neutrons are electrically neutral, the protons are positively charged, so the nucleus will have an overall positive charge. Okay, pretty simple. The electrons are outside the nucleus. They are not part of the nucleus. Okay, they are in fact quite away from the nucleus. Okay, so that kind of brings to an end the description of the nuclear model of the atom as determined by Ernest Rutherford. So I hope you found that video helpful, and yeah, if you have any difficulty with the content, please feel free to reach out to me.